Okay, today we're going to talk about one way to multiply two vectors together, okay? And this method is called the dot product. So here's the definition. Suppose we have two vectors. We'll call one of them v, and how about if we say that that is a comma b. So this is in R2, okay? And then let's say W. We'll call that C comma D. Okay, now if you want to do the dot product, we would write V dot, well, that's way too big, hang on. Dot W, and here's what it equals. Here's how you calculate it, okay? We take the first component of V times the second component of C. Multiply those together, you get A times C, okay? And then you take the second component of V times the second component of W. So we get B times D. And then you add those together. Okay, that's the dot product of V and W, or you could say V dot W. Okay, in 3 dimensions, it would look like this. Let's say V is the vector ABC, and W is the vector DEF. And you want to do their dot product. Okay, so what we do is, hold on a second here. Okay, so what we do is A times D get multiplied together, B times E gets multiplied together, and C times F gets multiplied together. So we get AD, BE, CF, and those get added up. That's the dot product in 3 dimensions. Okay, now one thing that's really important to understand is, what does the dot product require and what does it give you back? Okay, and what I want you to notice about that is the dot product requires two things, and then gives you one thing back. Okay, what does it require 2 of? It requires 2 vectors. Oops. And what does it give you as an answer? What kind of object? It gives you a number, right? But remember, what are we going to call numbers in this class? We call them scalars. So a dot product takes in 2 vectors and gives back 1 scalar. Okay? And because of that, dot product is sometimes called scalar product, because that's what it gives you. It gives you a scalar. Now, here on the screen, we have some properties of the dot product. Okay, property number 1 is the commutative property. We have 2 vectors here, u and v, and it says u dot v would equal the same thing as v dot u. Well, it certainly would. You can look over here at these two examples that I drew here, you see that it would not have mattered what order I did those in. I would get the same answer. For instance, look at the top one in 2 dimensions. It says v dot w equals ac plus bd. If I had done w dot v, I would have gotten ca plus db. Well, that's the same number, isn't it? You get the same answer either way. Okay? Let's look at the second property over there. Is the distributive property. If you have 3 vectors and you want to dot one vector with the sum of the other 2, you will get the same answer as if you do the sum of the dot products of the first vector with each of the other 2. And that's seeing that that's true, it's simply a matter of just writing them both out. Just write down 3 vectors, okay, and calculate this, and you'll see that they come out the same. They always will. Okay, the third property doesn't have a name, but it's saying that if you scale a dot product, you will get the same answer as if you scaled one of the vectors and then dotted it with the second vector, or scale the second vector and dot it with the first vector. And again, that's simply a matter of writing that out in the 2 different ways, or actually 3 in that case, and seeing that it comes out the same, no matter which of those 3 ways you were to write it. Okay, 4 is relatively obvious. Any vector dotted with the 0 vector is going to give you 0. That should be obvious. For instance, over there on the left, suppose that vector v was the 0 vector. Then that means a and b would both be the number 0, and so the answer there that you get from the dot product is 0. Right? Okay, and then the last one is super important as well, and it's not obvious, but when you write it down, it becomes obvious. If you dot a vector with itself, you get the square of the norm. Let's try that out with our vector v over there on the left. Let's see if that's true. So first, let's remind ourselves about how to calculate the norm. What's the norm of vector v? So remember, that's the square root of a squared plus b squared. So what's the norm squared? Would be a squared plus b squared. Now, what is v dot v? Well, that's a times a plus b times b. See, look, these 2 things come out to the same number. Any vector dotted with itself will give you the square of its norm. Okay? So that's really, really important. Remember that. The other 4 are also important, but number 5 is very useful. Okay, now, what are you going to use the dot product for? Well, here's one of its very nice uses. Suppose you have 2 vectors, okay? Let's call that purple one u, and let's call the green one v. All right, suppose you want to find the angle between u and v. It's very surprising to find out that you can use the dot product to calculate that with this theorem. Let's look at what it says there. U dot V equals the norm of U times the norm of V times the cosine of the angle between them. That's very useful, okay? So let's find, that's both in 2 dimensions or 3 dimensions would work the same way, okay? So how would you find theta then? Okay, if we have the norm of U times the norm of V times cosine of theta equals U dot V, that means that cosine of theta equals U dot V divided by the product of their norms, which means that theta is the arc cosine of that number. Okay? So let's use that to do this example here. Okay? We have 3 vectors given to us, u, v, and w. This is in 2 dimensions, okay, but it works exactly the same in 3 dimensions. And they ask us to find 3 angles, alpha, beta, and theta. Okay, so let's do that. The solution's already started. I have it typed out there what the norm of each vector is. Okay, let's check those and make sure those are correct. The norm of u is the square root of 3 squared plus 1 squared, so that'll be the square root of 10. That's correct. The norm of v is the square root of negative 2 squared plus 6 squared, so that'll be the square root of 40, which is 2 root 10. That's correct. And the norm of w is the square root of negative 4 squared plus 3 squared, which is the square root of 25, which is 5. So those are correct. Okay, now let's start by finding angle alpha. That's the angle between u and v. Okay, so I'm going to write the formula down. U dot v equals the norm of u times the norm of v times the cosine of angle alpha. Okay, now what's u dot v? Well, we better find that. U dot v will be 3 times negative 2 plus 1 times 6, which equals what? 6 minus 6, which is 0. So we have 0 equals root 10 times 2 root 10 times cosine of alpha. What's that tell us? It tells us that the cosine of alpha is 0. So how big is alpha? Alpha is 90 degrees, or pi over 2 radians. You see how that works? Let's find angle beta. Beta is the angle between V and W. Okay, so we don't have to erase everything we've done here. Let's just take the U and change it to a W. Okay. So now we will find U dot V. I'm sorry, W dot V, I meant to say. Okay, so that'll be -4 times -2 plus 3 times 6. So that'll be 8 plus 18, so that'll be 26. So we have 26 equals 5 times 2 root 10 times cosine of beta. So 26 equals 10 root 10 cosine beta. So the cosine of beta is 26 divided by 10 root 10. Now that's not one of the cosines that that we know. Like what I'm saying is it's not 1/2 or root 2 over 2 or root 3 over 2 or 0 or 1. So that becomes a calculator problem then. Find the arc cosine. Sorry, wait a second. Find the arc cosine of that number. That's something you would put into your calculator. Nobody's going to know that off the top of their head, okay? And it comes out to be approximately 0.6055 radians, which is about 34.7 degrees. Okay, you see how that works? It's pretty repetitive. I don't think we probably need to do theta like they asked, because we've done 2 and the third one is done exactly the same way. Besides that, we already found alpha and beta. Theta is just going to be the sum of those two anyways. So let's move on. Now, you remember this problem here that we did a minute ago, finding alpha? Look at that again, okay? And we had u dot v came out to be 0. Alpha is the angle between u and v. U dot v equaled 0. So we had here 0 equals root 10 times 2 root 10 times cosine alpha, which means cosine alpha is 0, which means alpha is pi over 2 radians, or 90 degrees. So that means that u and v are perpendicular. Okay, but we don't use the word perpendicular. Instead, we use the word orthogonal. We say u is orthogonal to v. That word orthogonal means perpendicular. You could also say v is orthogonal to u, or you can say u and v are orthogonal to each other. And a lot of times people, if they say it that way, we just say u and v are orthogonal. You don't normally put on the 3 words to each other, but technically that's what you're saying. Okay? Now, there is a test for orthogonality. And the test is you test to see if the angle is 90 degrees. But the point is, you don't have to do all of that. You only have to do it part way. to get your answer, because let's look at this. Let's look at this. Why did this answer come out to be 90 degrees? That's my question. Why did that come out to be 90 degrees? The answer is it came out to be 90 degrees because the cosine was 0. Now, why was the cosine 0? Did it have anything to do with that number? Did it have anything to do with that number? The answer is no on both of those. The only reason the cosine was 0 is because that number was 0. And where did that come from? That came from right here. In other words, this over here. So you see that you can tell if two vectors are orthogonal simply by checking their dot product. If the dot product is 0, then the vectors are orthogonal. So we can actually define the word orthogonal to mean that the dot product of the two vectors is 0. Okay, but spatially, what does that imply? It implies that the vectors will be perpendicular to each other, but we don't use the word perpendicular, we use the word orthogonal. Okay, and let's move on. So, next. Let's suppose you have two vectors. In fact, let's go back to the same picture we were looking at earlier. Okay, let's look at that picture here. We saw this picture earlier when we were talking about something else, but I have changed the names. Earlier, the green one was V and the purple vector was U. I swapped those names. Okay, now, what if you want to do this? What if you want to find what I call the shadow of U on V? Okay, what does that mean? What if you draw a perpendicular line here, as though you were holding a flashlight orthogonal to V, shining the flashlight straight down at V. Okay, what shadow would you cast onto V? Let's draw that. It would look like that red one, right? Let's just label that as W. Now, I want to show you how to find that vector W if you know U and V. Okay? So one thing we already know is we already know that U dot V equals the norm of U times the norm of V times the cosine of theta. That's one thing we know. But we also know this. Let's do a little bit of geometry now. Look at this right triangle here. Oh, by the way, I didn't mark theta. Let's do that. Here's theta. Okay, now, just because of basic trigonometry, I also know that the cosine of theta is the length of the adjacent leg. What is that? That's the norm of W divided by the length of the hypotenuse, and that's the norm of U. Now I'm going to take this and put it right here. And that's going to give us u dot v equals the norm of u times the norm of v times the norm of w divided by the norm of u. We get some canceling there. And what are we left with? U dot v equals the norm of v times the norm of w. Okay, now let's leave that there for a minute. And let me ask you a new question. How would you turn v into w? They're parallel, right? Which means w is a scaled version of v, right? Let me write this down here. Since w lies along v, we can get w by rescaling v. Okay? In particular, w equals v times the scalar, which is the ratio of the norm of w times the norm of v. Okay, let me walk you through that. If you start with v, okay, start with v. Now, divide that by its own norm, which means multiply v times the scalar 1 over the norm of v. Now you will have a vector in the same direction as v, but with length 1. Now if you take that vector and multiply it times the norm of w, you will have a vector in the same direction as v, but with the same length as w. Now, w does lie in the direction of v. So if you have a vector in the same direction as v, but with the same length as w, then what you have is in fact the vector w. Okay? That's where I got this from. And this is always true. If you have two vectors that are pointing in the same direction, and you want to turn the first vector into the second vector, all you have to do is multiply that by the ratio of their norms. Okay? All right, so where is this going? Let's get rid of this stuff here, and then I'll cut to the chase. So let's take this right here, and let's work with that. Okay, I want to rewrite that like this. The norm of W times 1 over the norm of V times vector V. Okay, and now I want to use this right here. What does the norm of W equal? You can see that the norm of W equals U dot V divided by the norm of V. So that gets us to here. Now, what's the norm of V times the norm of V? That's the norm of V squared. So we have U dot V divided by the norm of V squared times vector V. Now, remember, the norm of V squared is V dot V. Here's the formula we want. W equals this. Okay, look at that for a second. I'm going to zoom back in on the picture and I'm going to write that down. Okay. So that red vector is U dot V divided by V dot V times the vector V. Okay, and that has a name. That's called the projection of U onto V. And we'll write this PROJ with a subscript vector V and then a vector U here. That's the projection of U onto V. Okay, and I'm going to put that formula in a box. Okay, there you go. That's very important formula. The orthogonal projection of U onto V equals U dot V over V dot V times the vector V. Okay, and we can even take this a little bit further. Let's not leave out that black, what is a line segment now, but let me turn that into a vector by putting an arrow here. Look, the green vector U is the sum of the red vector plus the yellow vector, the black vector. Correct? You see that? If you want to give those some names, we can go back to calling here. We can go back to calling that red vector W if you would like for now. What should we call the black vector? Let's call that vector T. Okay. Do you see that U equals W plus T? That's correct, right? You can tell that from the picture. This is an important concept. What we've done there is we have decomposed U into two vectors that are orthogonal to each other. That's called an orthogonal decomposition of U. Okay. And what is W again? Do you remember? W is called the projection of U onto V. What would T be? Well, this might sound like a lazy way of doing it, but it is in fact the truth. T is U minus W. So T is U minus the projection of U onto V. Okay, so we have U equals, now we have a formula for that projection. Remember, it's U dot V over V dot V times the vector V. Okay, and that is parallel to V. And then here we have U minus that. And that portion is orthogonal to V. So given any two vectors, you can break one of them up into two orthogonal vectors where one of them is pointing in the same direction as the second vector that you were given. And that's called an orthogonal decomposition. And let me put that here in a box for you. Okay. And that's the end of this lecture.